the way I think about it is, I mean, this is not the only way, but the way I think about it is that reagents can be used to figure things out. You got a strong reagent, you have a weak reagent, right? That's possible. Strong reagents make things go faster, so probably it has a pretty much dominant factors there, higher reactivity than weaker reagents. But strong reagents, strong base, makes the E2 and SN2 both possible. So having a strong reagent doesn't mean that it's going to make only SN2 or it's going to make only E2. Both SN1 and E1s are possible. Only thing it doesn't do is an SN1 E1, right? That's only the weak reagents. So at least the reagents can figure out it's going to be bimolecular reactions or unimolecular reactions. That can be sorted out. How can figure out strong reagents? Either that's going to happen with an SN2 or E2. That has to do together with a substrate. If you have a strong nucleophile / base, meaning that something that can act as a strong nucleophile, also a strong base, but if it's reacting with a primary alkyl, the one with the predominant products, substitution reaction. Because the tertiary alkyl halide is better for the E2, not good for the E1, E2. So primary is good for the SN2, not good for the E2. So your substrate could be for the SN2 there. If in the tertiary alkyl halide with a strong nucleophile / base, what reaction will take place? SN2? It's going to be E2 because SN2 doesn't happen well with the tertiary alkyl halide. So it's not just this one. You also need to look at the alkyl halide side. These are pretty good. They matches their preference together, so you can clearly, they're limiting down that only one pathway. But the problem is secondary. Secondary, either is possible. SN2 is possible, E2 is possible. Does it mean they're always both competing? I mean, truly, if they're both competing, then yes, we'll get mixture. But it's probably not going to use to make this a possibility, right? So this is where this concept goes in. What if your reagents given can be a strong nucleophile, but not a strong base? You use that with a secondary alkyl, then you should expect SN2, right? Because if it's not a basic, then you can have an E2 elimination possible. So somehow, if you can figure out your reagent can be strong, it's a more preference to be a nucleophile than a base, then you can narrow things down. The other way is possible. You have a reagent, not a strong nucleophile, but strong base, then you're going to have an E2 elimination reaction, even with the second. So that is something that you need to figure out. And obviously, even for the E1 and E2, it's really hard to sort these things out because they always comes together. But there's one occasion that you can probably narrow things down. In order to make a double bond, you need to have an adjacent hydrogen, right? That is a given. If there's no adjacent hydrogen, no rearrangement is possible, then you can only have an SN bond. There's no other way. So that is probably a situation that limited down to SN1 only. I'm pretty sure that there might be another occasion that I can write it down, but these are probably most of the scenario that you need to think about. This is kind of tricky, isn't it? So this is what I'm going to show you in the next slide. We have a cyclohexyl bromide. This is a secondary bromide we just talked about. With that, strong nucleophile, strong base. So the methoxide, small, strong nucleophile, that is another hydro base, strong base. I'm expecting that make an SN2, that make an E2, both will take place at the same time. They're really competing. If you're using an alcohol, weak base, weak nucleophile, then with that, only SN1 E1, right? That's something that we can expect. So this is the products of an E1 and SN1. So this is a kind of issue. We cannot sort it out what goes where, how it goes. Unless reagents can be classified as a strong nucleophile, not a good base, or strong base, not a good nucleophile, right? So that's why I'm asking you to remember these things. That is something you can consider. It's a strong base, but not a good nucleophile. Why? Because it's bulky. It's a big, huge substituents. surrounding the basic center, makes it sterically demanding, which is not good for the substitution reaction. So if you're using p-butoxide, if you're using diisopropylamine or diisopropylamide forms, or triethylamine or these are dimethylpyridine, all of these are common bulky strong base. If you're using this with that, should I expect SN2 reactions? It's a bulky base, so SN2 is not going to happen. You only get an E2, even though you can potentially have an SN2 possible with the smaller reagents, but with this bulky big base, you can only expect an E2. So things are limiting down for you. You need to understand why it happens in this case. So that's why I ask you to remember, this is a typical example of the bulky base. Then the other situation, in order to make only SN2 with it, that reagent has to be strong nucleophile, not a good base. Do you remember any of these type of reagent that is strong nucleophile, not a good base? Most of the time, strong base becomes a strong nucleophile. But I'm asking you to find the ones that is not a basic, but good nucleophile. Have you ever seen that? So you're kind of trying to remember what sort of a nucleophile you have seen it. But let me say time for you. Cyanide is a salt. This is not basic. Sodium cyanide, if you dissolve in water, you take the pH, it's going to make it 7. It's not basic at all. But cyanide is really strong nucleophile. So you got strong nucleophile, not basic, with a secondary alkyl halide, you should only expect SN2. And with the primary, of course, you get SN2. If you give this for the tertiary, still no SN2 because the tertiary is really bad for the SN2, right? What other reagent can be considered as a strong nucleophile, not a good base? This is the azide, 3 nitrogen put together with the negative charges. There's a salt as well, not a base. Well, this is kind of a little tricky. Thiolate, it has a moderate basis state, but not a strong one. Because it's a sulfur negative charge, more stable anion basis, it drops significantly compared to the oxygen versions. So these are really good nucleophile. Why? It's a soft, polarizable nucleophile. Remember that? SN2 reaction goes well with the soft, polarizable, big nucleophile. So that makes the SN2 reaction way better than it's a moderate, small basis state, but like I said, strong nucleophilicity brings it out, in my opinion. And then carboxylate, that, remember that oxygen negatively charged typically makes it basic, but this will make a resonance structures that weaken the basis. So that becomes like a nucleophile better. I mean, these two are the less obvious choices, but those two are really good nucleophile, not a basic at all, zero basic. So something that you can use to sort it out when there's a possibility, right? Substrate can narrow down, reagent can narrow things down. So I want you to remember that. All right. One type of question can really make it off balance could be the intramolecular reactions. There's no reagent there, so nothing happens. Typically, you see reagent like this, there's nothing here. You have to remember that there is an alkyl halide on this side of the molecule, there's a nucleophile on the other side of the molecule. Things can happen within the same molecule. That is attached by this end, make a 1, 2, 3, 4, 5 member ring after kicking the chlorides out. That's going to make this. This is something called the intramolecular reactions. It's kind of not easy to figure out because it's kind of a snake biting its own tail, but you make a cyclic structures. But you gotta see it. This with that, I mean, this is not a nucleophile, that is not a nucleophile. If you react with this one first, either will happen first. This will come, attack this one, you get that forms. But it's not going to stay like this. That's the first thing it forms. Then what happened after that? That is seeing that one. That attack the other end, just like we see here, and then that's going to make this one. The intramolecular reactions. Same thing with that. This one can attack either first, It's going to attack and then make a nitrogen substitute in this position. Then immediately sees another one down there, so that makes a bond here. And then that goes further out, and you're going to get a cyclic structures like this. So intramolecular reactions are a bit tricky because you have to see how it goes probably over the fields. Time below. Okay, that's something that we already talked about. We talked about the stereochemistry. These are the strands here. The cis, same hydrogen, the same anti-nuclear. You can only form this, let's substitute double bond, or because of this hydrogen in the same side as this one, but attached with strands hydrogen, right? It's the same thing.